Hello class, this is lesson 5.5. Here we look at equations that involve logarithms and exponential functions. So we will just dive straight into examples here because in the previous sections we learned about logarithmic functions and exponential functions. Now we just solve equations involving logs and exponents. So for an example, we may see something like 6 raised to 3x equals 36. Okay, so how do we solve for x when x is in the exponent? Well, in this particular example, it's nice because we can rewrite both sides to have the same base, and that's just because in this example 6 squared equals 36. So the right hand side can be written as an exponent with base 6, and the left hand side is an exponent with base 6. And once we get the same base, we can set the exponents equal. And now we can only do this when we have the same base, so we do not always have the same base, but this example was cooked up in a way so that the left hand side and the right hand side can be written as base 6 exponential. Okay, so let's look at another example where we do not have the same base on both sides. Say we have 3 to the 4x minus 5 equals 7. Okay, so now that we cannot write this as a base 3, right? Like, for example, if it was 9, you could write 3 squared equals 9. But we can't find a very easy way to write 7 as a 3 raised to something. So what we can do in this case is we take the logarithm of both sides. So on the left hand side we have 3 raised to the 4x minus 5. On the right hand side we have 7. So we could take a log of both sides, and I'm going to choose to do log base 3 on both sides. You don't have to choose that logarithm, but the reason I chose it was so that this log and that exponential will cancel out nicely, so that the left hand side turns into 4x minus 5. And then the right hand side remains messy, it's just log 3 of 7. But the right hand side is just a number, so we're solving for x. We want to find what number x equals. So we add the 5 to the other side. We have 4x equals log 3 of 7 plus 5. And then we divide the 4. And we get log 3, 7 plus 5 over 4. And that is just some number. Now, if you chose to take a different base, right, say you did base 7 on both sides, your answer would symbolically look a little different, but if you slapped it into a calculator, it will equal the same value. So let me just demonstrate that. If you took log base 7 of both sides, you would have this, and then you'd have these guys canceling out. So then you'd have, on the right hand side you have 1, because log 7 of 7 is 1. And then on the left hand side you bring the exponent out front. That was just a property of logarithms. Right, one property of a logarithm is you could pull the exponent down. So that's what I did in this step. Okay, so now we multiply the left hand side out. And then we solve for x. 4x equals 1 plus 5 log 7 3. forgot to, it's 4x times log 7 of 3. 4x is log 7 of 3. Okay, so then when we solve for x, we divide the 4 log 7 of 3. Okay, and the reason why I did this was just to demonstrate that this should equal the same thing as this, even though they look different. Because here when I solved, I took log 3 of both sides, which made the equation really clean and easy to solve for. But I could have taken log 7 of both sides, I could have taken log 9 both sides, any base you want, but some bases look better. So even though the answer is unique, the symbols you use may look different depending on which logarithm you choose to use in these equations. Okay, let's look at some more examples. Say we have 9 raised to x squared times 3 raised to 3x equals 9. So this is another example where the left-hand side and the right-hand side can be written with the same base, because 9 is really 3 squared. So 9 to the x squared is the same thing as 3 squared to the x squared. Right. And then on the right-hand side, instead of the 9, we can write 3 squared. So we can write everything in a base 3 format. And now we just multiply it out using some properties. Here we use the property where a raised to some number and then you raise it to another number. It's just the same thing as a raised to the n times n. Right, so we have 3 to the 2x squared times 3 to the 3x equals 3 squared. Okay, and now we need to multiply this out. We'll use the property where a to the n times a to the m equals a to the n plus m. So these are two properties we can use. So we get 3 to the 2x squared plus 3x equals 3 squared. And now since the left-hand side and the right-hand side have the same base, we can set the exponents equal. And then we just solve this equation. So put everything on one side and then plug into the quadratic formula. So we have negative 3 plus or minus the square root of 3 squared minus 4 times 2 times negative 2 all over 2 times 2. So negative 3 plus or minus the square root 9 plus 16 all over 4. Negative 3 plus or minus square root of 25 over 4. Negative 3 plus or minus 5 over 4. So negative 3 plus 5 over 4, or negative 3 minus 5 over 4. 2 over 4, or negative 8 over 4. So 1/2, or negative 2. Okay, let's look at some more problems. Say 12x equals 4x plus 1. So this time the bases are not the same, so let's just take a logarithm both sides. So I don't know which one you want to do. Say we take log 4 of both sides, log base 4 of both sides. Or just for fun, I guess, let's use a different logarithm, just because I want to demonstrate that you can pick any logarithm you want. So I'll take the natural log of both sides, since that's the most used logarithm. Okay, and now we'll use the property where we can bring the exponents down. Okay, so now we have x times log 12 equals x plus 1 times log 4. Okay, and these are just numbers. They're constant numbers, so don't let those trip you up. We're solving for the variable, and everything else are numbers. Okay, so we have x log 12 equals x log 4 plus log 4. So in this step I multiplied it out. Okay, put everything with x on the same side. So I'll minus the x log 4 to the left hand side. Okay. We can pull an x out of both of those two terms, leaving us with x times log 12 minus log 4. And then on the right hand side we have log 4. So solving for x, we have log 4 over log 12 minus log 4. Okay, let's look at another problem here. Let's solve this problem. Log base 10, which we usually do not write the 10, of x is -3. Okay, so if the x is inside of the logarithm, how do we solve that? Well, what you can do is exponentiate both sides, right? You could do 10 raised to the log x equals 10 raised to the -3, right? So we're allowed to do that. And since a logarithm, when we don't write a base, is really base 10, now these guys are going to cancel out, and we get x is 10 to the -3. Which, you may need to put that as the decimal. Okay, let's try solving another example with logarithms. Say we have log base 10x plus log base 10 x plus 3 equals 1. So if we want to solve for x, first we could use the property where adding two logarithms is the same thing as the logarithm of the product. Right, this was a property we learned last week, where the log of a product is equal to the sum of logs. Okay, so we just use that. Okay, and then we can, so there's two ways of thinking about this. You could either exponentiate both sides, or you could go back to the definition of a log. So remember, log b of a equals c. By definition, that means b raised to c equals a. Right, so therefore 10 raised to the 1 will equal x times x plus 3. Right, so 10 raised to the 1 will equal x plus 3. 10 equals x squared plus 3x, or x squared plus 3x minus 10 equals 0. So x will equal -3 plus or minus the square root of 3 squared minus 4 times 1 times negative 10 all over 2 times 1. Negative 3 plus or minus the square root 9 minus, plus 40 all over 2. Negative 3 plus or minus square root of 49, 7, 2. Negative 3 plus 7 over 2. For negative 3 minus 7 over 2. So what do we have? 4 over 2, or negative 10 over 2, 2, 4, negative 5. Another example, log 2 of x plus log 2 of x plus 1 equals log 2 of 6. Now this is a nice example because we have the same base on both sides. But first we're going to have to rewrite this sum as just a single logarithm, which is something we learned last week. Right, the log of a product is the sum of logs. So last week we learned that the log of a product is equal to the sum of the logs. So maybe review last week. So you may need to review the formula last week. Log of a product equals the sum of the logs. Okay. And now here, since both sides have the same base, we can set the inputs equal. We could set this equal to that. Right, so x plus 1, 6. Now I was only able to do that because both sides were base 2. Otherwise we would be out of luck. Okay, so we have x squared plus x equals 6. X squared plus x minus 6. So what do we have? Let's just factor this one instead of using the formula. On x plus 3, x minus 2, x equals negative 3 or 2. There's also one thing I forgot to mention in the last example. We have to make sure our solution is in the domain. Now know that you're only allowed to plug in numbers greater than or equal to 0 into logarithms. So since we're plugging in x into this log, x has to be greater than or equal to 0. We plug in x plus 1 into this log, x plus 1 has to be greater than or equal to 0. Right? Now, because of that, that means this solution is not in the domain. So we have to throw that solution out. Similarly, if we go back to our last problem, we have to plug in numbers bigger than 0 or bigger than negative 3. So we actually have to throw away this number. It was a solution to the problem, but it was not in the domain of the original equation. So we have to be careful about that. Right, if I draw a picture of a logarithm, it looks like this. Right, log x. So clearly the domain of a logarithm is all the numbers greater than 0. So when you solve the equation, sometimes a solution will be over here, but it's not in the domain, so you have to throw that solution out. Okay, and with that we can end today's lesson on 5.5. Thank you.